Okay, so now we are going to study homework 5. Homework 5 is about hypothesis testing. I had to make a, so I admit that this question will be really difficult, uh, but this is the simplest possible example I could make, right? So there is only one regressor. Let me explain what we do. Of course, pause the video if you haven't read the homework. Uh, like read the homework first and then listen what I do. So basically, the simplest possible example is linear regression with on our one regressor, mean zero, there is no intercept, and we are not sure if this regressor is the only regressor there, maybe endogenous or maybe exogenous. So we have a scalar uh, instrument. So we have an instrument, so we could use IV regression model, or if X was exogenous, then we can use OLS. So we would like to test it. That is the key idea. And basically, the key assumptions are pretty much the standard. Like all the nice assumptions are put. And as I said, so this is the simplest possible example I could make. So anyhow, you need to do this by yourself at some point. So I made it a question. And the first two part A and part B are kind of preliminary, like CLT, central limit theorem result, which I'm going to discuss later. Let me start from part C. Part C is about unrestricted model and D unrestricted estimator. Part E is wild test, and part F is about part F is about wild. Part G is restricted model. H is restricted estimator. I is about J-test, criterion-based test. J is asymptotic distribution for that. K is Hausman test, like and L is Hausman test, like that. So, like let me start from the unrestricted and restricted model, right? It should be simple. So we have like, let me use, this is a new file. So I will reset what we have done. Increase, change the margins like that. So, unrestricted model, we have very simple, the simplest regression model with uh, with excuse me, why? Oh yeah. So with an instrument Z, uh, assume that all variables are mean zero. So there is no intercept, that does not matter. And of course, y, x, z, all are scalar, one-dimensional. So everything is simplest possible case. And then we want to test null hypothesis that x is exogenous versus alternative hypothesis that x is endogenous, okay? Here then, we can think about two different cases. Say, let me put section here. Unrestricted model and restricted model. Unrestricted model, the unrestricted model uses assumes that X is endogenous and uses Z as an instrument, right? And restricted model, in the restricted model, we use we take the hypothesis, take the null hypothesis as an assumption so that X is exogenous, and we can use, we do not need an instrument, right? So it is pretty clear what you are doing. And part C, let's have a look at part C. The moment function for the unrestricted model is given by this. Using this moment function, set up the sample GMM criterion function, right? Like pretty simple, like consider GI, I will use this notation. We will use this, okay? So I skipped like the simple part. U here, superscript U means unrestricted model. Meanwhile, the restricted model has similar but different moment function, okay? Then, of course, so the sample average, sample moment function is, sample mean of the moment function is, say, U like this, okay? And so the restricted model has similar sample moment function. Okay, and remember that we do not need any weighting matrix for GMM estimator because there is only one moment condition for one unknown parameter. So if you have equal number of equations for the unknowns, so you don't need to worry about the weighting matrix. We have studied this in homework 4, okay? So the GMM criterion function is given by, say, Q U. Actually, it is simply its square because there is no weighting matrix is not needed. So you can simply just take its square, okay? And then um, you can calculate, minimize, like let's do, and here in the restricted model, we can do the same thing. The GMM criterion function is like this, okay? And now you have to solve it, right? So, by the way, well, let's think about this first. In the restricted model, let's think about this problem. You may think it's OLS, right? In the end, it is right. OLS, but it is actually not the OLS. So based on our definition, this is what we have. But so we are going to minimize this guy. We are going to minimize this guy. It is different from the OLS criterion function. That OLS criterion function looks like this. here you have to square inside the summation. We like if you square and then sum, that is well as least squares estimator. But here we square after summation, taking summation, right? So they are technically they are different, but in the end you will see the results are the same. The minimization results are the same in the end. But by the way, let's have a look at let's think about the unrestricted model now. Similarly, its square is going um, outside, right? So we have this. Now its derivative, simply let me just write it simply like this. The derivative, uh, the derivative looks like 2 times uh, minus 2 times this times same thing again. Okay, that is this is the let me see, is it right? I believe it's right. Or okay, I think I got a better idea. So using the notation given in the question, you may rewrite this as in the question I gave you this notation AZY minus AZX beta, right? It's this is better. In the question, actually I wrote like this. We have summation, like basically you can rewrite this as summation of the average of zi times yi minus beta times sample average of zi times xi. So the sample average of xz is written this way. Sample average of z times y is written this way, right? So you can find the notation in the homework, and then its derivative is much easier to calculate. So it is a very simple two quadratic functions derivative. So we are going to have 2 times hat a zx beta minus 2 times hat a zx times hat a zy is the derivative. Okay, let me see. Here square. You have to square there, and the first order condition is, so this derivative equals to 0 when beta is beta hat. So 0 equals 2 times I'm going to denote it as like say u because it is unrestricted estimator, right? And from here, if you solve for beta u, we obtain at beta unrestricted model as hat a zy hat a zx. So we have a closed form solution here. Right? So this is a very familiar formula from the instrumental variable regression model. GMM, in the end, gives you the instrumental variable regression. And you can do the same thing here, right? Of course, this is OLS, but you have to use this one. In the same way, just replace the subscripts, and then you can obtain, say, hat beta restricted model. The restricted model's beta is xy divided by xx. Okay, so like just replace z with x, and then you get the OLS, right? Right. This is the OLS formula when all the variables are mean zero, right? If everything is demeaned, then you get this formula. Okay. So this answers a few questions. Let me see what we have to learn. Okay. Now then, let's think about we just tried. Uh, we just did C, D, and now let's think about the wild test. From wild test, we are testing the null hypothesis is z xi, right? Like we would like to test it. So in our estimation using the unrestricted model, if the null hypothesis is true, uh, we can this will be close to zero. So intuitively speaking, we will have this. Uh, that is so. So we are going to test if this is close to zero or not. That is our testing idea. So we can we construct the wild test as n times this prime. Usually you have to take transposition, but here it is one-dimensional, so you don't need to worry about that. So, and the same thing, right? And we know that this guy follows chi square, chi square 1, because this is just one-dimensional hypothesis. So we know the limiting distribution will be chi square 1. By the way, because everything is one-dimensional, the reason why I introduced chi-square is because this is, I explained this as a distance in vector space. When you have vector space, we have to think about distance as a quadratic function, right? But now everything is scalar, so you don't need to use chi-square actually. You can just directly apply the t statistic if you are willing to try that. That is possible. Then actually that is better. That'll be easier. But just I will follow the chi-square setup because this is more general. Okay. And then the main problem is how to find the asymptotic variance, where we have to find that using this formula. So let's rewrite epsilon. This can be written as, obviously, epsilon hat is yi minus beta unrestricted beta times x. Okay, so so you can rewrite everything like this, and using the notation I introduced above, we may rewrite this as, so unrestricted beta was this guy. So copy it and place here times like this. Okay, this is uh, our test statistic, the basis of our test statistic. We want to show that this guy, after multiplying square root n, we would like to show that this guy converges in distribution to normal 0v under the null hypothesis. So under the null hypothesis, this will be expectedly 0. Expectation of this guy will be 0. So there you don't need to subtract the mean, and we hope this to converge to something very nice, normal distribution with variance p. How can we do that? We are going to we do that in part A, right? Part A is part A and part B is the derivation for this guy, right? I will do that later, okay? I'm going to delay that until after I explain the other test statistics, right? So it will be pretty tedious algebra. So let me skip that for now. Okay, I will stop this video here and I will continue the next part in the next video. Okay, see you later.